video contains aliens, sniffer dogs, some beeped out curse words, more aliens, really bad acting. I mean really bad. Did I mention the aliens? There is unrest in the universe. A race of evil space lizards known as the Inane Cult are planning to take over Earth. Their leader, Lazink Dirt, is poised for the invasion. His trusted second-in-command, Tunic Lane, boards his spacecraft and heads off with an update for his leader. Meanwhile, Horistet, a brave but exhausted saviour of our world, is oblivious to Lazink Dirt's plans. He has spent many years protecting the Earth, but he is counting the days until he can pass on his mission and retire to a nice beach. His heroic protege, Days Flitch, who has been spying on the Inane Cult, hurries across the galaxy and arrives with an important message for us all.
Horistet, I'm so glad to see you. Days? It's so good to see you. I'm so tired of fighting this war. I don't think my body can take any more. Where have you been? I've been on a long, dangerous, heroic mission where I was very heroic. I have intercepted a transmission from Lazink Dirt, leader of the Inane Cult. It's not good news, I'm afraid. What is it? Let me show you.
Tunic Lane. The shape-shifting training is going well, I see.
Well, yes, it's going very well, except I can't get my hands to become humanoid. I can do the face, the body, but the hands, I can't do the hands.
Is the invasion fleet ready?
Nearly. The shape-shifting training has been successful on about half of the alien fleet. But the other half, they just can't get the hang of the shape-shifting. They can't do it.
I grow impatient for victory. Those that can't shape-shift into humanoid form shall be sent in their natural lizard form. The humans will never notice.
As you command, mighty leader.
Oh man, that is bad. Horror, how can we stop them? Well, while you've been away, we have been experimenting with training sniffer dogs to detect aliens, but we need more research. Can you get me some sniffer dogs? I found the best spaniels we have, but we only have 8 of them. That's not many. I don't know what I can do with that. I need to consult a higher intelligence. What you need is a repeated measures design. Well, the all-knowing Professor Hippo has told us that to get some kind of answers with only 8 dogs, we're going to need to use repeated measures designs. So we best get on with it. Now, repeated measures design, we can analyze again with a linear model like all the other designs that we've looked at on this module. And we're addressing a scientific question, which is whether we can use sniffer dogs to sniff out aliens. We've got a sample of sniffer dogs, a small sample, only 8 of them. We're going to need to test them. We're going to need to collect some data from them. We'll visualize that data and then we'll fit some variant of the general linear model. And in doing that, we're going to estimate parameters. We could look at confidence intervals of those parameters, and we can test hypotheses. Is it the case that sniffer dogs can differentiate humans from aliens? we're going to have to test assumptions of that model. We're going to have to test we're going to have to fit robust versions of those models if the test assumptions aren't met. Everything is the same as what we already know. The only difference is that we have a different kind of design, a repeated measures design. So let's get on and have a look at what that actually means. Okay, let's think about the simplest experimental design that we could use to test whether our sniffer dog training had worked. Now, our sniffer dogs have been through a training regime where they are rewarded when they make vocalizations when they're sniffing the thing that we want them to sniff. So essentially what we do is we put an alien in front of them. When they're sniffing that alien, if they make a little noise, we give them a little treat. So they get used to the idea that they get rewarded for making noises when they're smelling an alien smell. And then when they're smelling a human, we don't give them any treats for vocalizing. So hopefully, if the training is successful, they're able to differentiate an alien smell from a human smell. Over the course of the training, they'll be learning to make more noise when they're with an alien, because they think that if they make noise when they smell an alien smell, they're going to get a treat. So the simplest design we could use to test whether our training has been successful is to take two groups of dogs that have been through the training and randomly assign them so that some of them sniff humans and some of them sniff aliens. And we could measure how many vocalizations they make while sniffing. Now in this kind of design, this is the same sort of design that we've looked at in previous lectures. So we have different participants in different categories of the experimental condition. There's two types of variance. There's systematic variance, so there's variance in vocalizations in the outcome that is going to be created by our experimental manipulation. So in this case, it's going to be created by the fact that some dogs are sniffing humans, some dogs are sniffing aliens. So that difference should create some kind of variability in the vocalizations if the training has been successful. There'll also be unsystematic variation. We've got different dogs in the two groups, and dogs, for example, have natural differences in how much they like vocalizing. Some dogs are very chatty, as it were, and some dogs are not very chatty. So there's going to be some kind of differences between the groups, like naturally occurring differences. And there may be other factors as well, like when they're tested, you know, maybe if the dogs are particularly hungry in one of the groups, that could be a confound or something. So there'll be some kind of other variability in vocalizations due to factors that we perhaps haven't measured. So we always have these two types of systematic and unsystematic variance. Now, when we use repeated measures design, what we're doing is we are using the same participants in all of the experimental conditions. So in this case, we've got our 8 dogs that have been trained. That's all we've trained so far. And we need to test whether they can differentiate humans from aliens. So what we could do is we could test the same 8 dogs, get them to sniff a human and measure how many vocalizations they make, and at a different point in time get them to sniff aliens, see how many vocalizations they make. The design hasn't changed. All that's changed is that we're using the same dogs in each experimental condition. Now what this should do in theory is reduce the unsystematic variance, because by using the same dogs in the two conditions, well, we know those dogs have exactly the same propensity to vocalize because it's the same dogs, so there shouldn't be any difference there. We know their noses are going to be equally as sensitive because it's the same dogs, so it's not going to be the case that, you know, the dogs sniffing the aliens have more sensitive noses than the dogs sniffing the humans, because we're using the same dogs. So across that group, they have exactly the same sensitivity in smell. Yeah, that's probably a good enough way to put it. So by using repeated measures design, hopefully we are reducing the unsystematic variance. We're controlling a lot of factors across the experimental conditions. So the benefits of repeated measures designs are, on paper, they're more sensitive. So you should reduce the unsystematic variance because a lot of things are held constant across the experimental conditions because you're using the same participants. So you should get more sensitivity to experimental effects. We should have a more sensitive design to detect whether our sniffer dogs can differentiate aliens from humans if we use the same sniffer dogs. Hooray! The other good thing is it's an economical way to test experimental hypotheses because you need less participants. So in this case, I mean, 8 participants is still really, really small, but it allows us to at least test this hypothesis. If we had to divide those 8 dogs into 2 groups, a group that sniffed humans and a group that sniffed aliens, we'd only have 4 dogs in each group. That would be, you know, an awfully small number of participants. So it's a more economical design as well, because you need fewer participants. But you do have to be aware that participants can get fatigued. So if you're you know, subjecting participants to like hundreds and hundreds and hundreds of experimental conditions, they are going to get fatigued. The quality of their data is going to be poor. That shouldn't be a problem for us because we're only going to have a very small number of experimental conditions. Okay, so the design we have settled on, thanks to Professor Hippo's wise advice, is this. To test whether our puppies can sniff out aliens, first off, our outcome measure is self-evidently going to be vocalizations, because that's what we've been training. So we're going to let them sniff an entity for 1 minute and we'll count the number of vocalizations they make during that minute. Now, to test the hypothesis, we are going to vary the entity that they sniff. So on one occasion, they're going to sniff an alien, not in humanoid form. On another occasion, they're going to sniff a human, which is a control for whether they can detect aliens versus humans. We're also going to let them sniff a mannequin, which is a control for them sniffing something in humanoid form that's not a human. And we're also going to get them to sniff a shape-shifting alien. So this is an alien that is able to transform itself into humanoid form. So across these 4 different entities, the dog gets to sniff each one of them for a minute and we count the number of vocalizations. And for each dog, they'll sniff them in a different order. And that's to get rid of any potential confound of the order in which they sniff the entities. We also are going to have a variable to indicate the dog's name. And as you already know, there are 8 dogs in total. Here are the data. So we have our 8 dogs: Milton, Woofy, Ramsey, Mr. Snifficus III, Willock, the Venerable Dr. Waggy, Lord Centicle, and Professor Nose. And each score in each column represents the number of vocalizations they made while sniffing each of the 4 entities. So for example, Milton made 8 vocalizations while sniffing an alien, 7 while sniffing a human, 1 while sniffing a mannequin, and 6 while sniffing a shapeshifter. Now, a couple of things I want to note. First of all, if we look at the means for each of the entities, these are the things that our model is predicting. Essentially, these are the predicted values from the model. So we've got about 8 vocalizations when an alien was sniffed, about 4 for a human on average, about 4 for a mannequin on average, and just under 6 for a shapeshifter on average. So they're the predicted values from the model, exactly the same as in a between subject or independent design. So that's what we're testing. We're testing whether those values are different. So that represents our experimental effect. But I also want you to note that the different dogs vary in the effect that the experiments had. So for example, if we look at the Venerable Dr. Waggy, has scores of 7, 5, 6, and 7. So basically, there's kind of almost no experimental effect there. It doesn't matter what he's sniffing, he gives between 5 and 7 vocalizations. So it looks like for him, the training hasn't worked. And we can tell that because if we look at the variance in those 4 scores, so the variance across 7, 5, 6, and 7, it's pretty small, 0.92. So it looks like training hasn't had very much effect on the Venerable Dr. Waggy. Now if we take another dog like Professor Nose, who perhaps got his name because he's a very good sniffer, we can see that there is a lot of variability in the vocalizations that that dog makes across the entities. So when it's an alien, he does 12 vocalizations. When it's human, he only does 6. When it's a shapeshifter, he does 1. When it's a mannequin, he does 8. So the variance across those scores is huge in comparison to the Venerable Dr. Waggy. So for Professor Nose, it looks like he really has a lot of variability in his vocalizations depending on what he's sniffing. So the point here is there are individual differences in the effect that the experiment has had. There is variability in the extent to which the training has been successful. So for a dog like the Venerable Dr. Waggy, the training hasn't been very successful. His vocalizations are really pretty similar across the 4 entities. Whereas for, say, Professor Knows, it looks like the training might have had more effect. There's a lot more variability in the vocalizations that dog makes across the entities. So the point here is that the experimental effect is kind of embedded within the individual, and there are individual differences in the extent to which the experimental manipulation has had an effect. Okay. So this is what the data look like in R, just so that you're not confused by the previous slide. So we have it in long format. So you can see we have dog name as a column, and our first dog, Milton, takes up 4 rows, but those rows distinguish the different entities that were sniffed. So that's coded in a different column, and the final column for vocalizations shows the number of vocalizations he made for each entity. So this is known as tidy data format or long data format. This is just to illustrate that this is how the data are laid out, and we could scroll down and see some of the other dogs listed there, and you can see each dog takes up 4 rows because they sniffed 4 entities. So when we do a repeated measures design and we want to use the linear model, we have the same participants in all conditions, and so the scores across those conditions are going to correlate. As we've seen, the experimental effect is kind of embedded within the individual. And thinking back to the lecture on the beast of bias, we also know that there's an assumption that the residuals in the linear model are independent. Now clearly this kind of design violates, other things being equal, that assumption, because we would expect the errors now to actually be correlated, because the errors for when we're predicting scores for an alien being sniffed or a mannequin being sniffed, they're related to each other because they come from the same dogs. So they can't be sort of fully independent, because the extent to which a dog sniffs a human is going to impact how much they sniff one of the other entities, because, sorry, not sniff, vocalizes during sniffing one entity is going to affect the number of vocalizations they make when they sniff another, because dogs will vary in their natural vocalizations. So we'd expect, other things being equal, that the assumption of independent residuals is violated. So we need to adjust the model slightly to kind of estimate this dependency. And how we end up doing that is by essentially making the parameters a bit more complex than they were before. So ordinarily, if we just simplify the model and assume that the entity is a single predictor, in actual fact, entity will be split into 3 dummy variables or contrast variables. But let's pretend that's not the case, just to keep things simple. So let's imagine we're just predicting vocalizations from a single predictor of entity. As we've seen loads and loads of times before, ordinarily we'd have an intercept. So what's the level of vocalizations when the predictor is 0? And we'd also have a parameter estimate attached to the predictor variable of entity. Now all that's changing in this kind of design is that we potentially can allow either of these parameters to vary across individuals. So notice, instead of being called beta 0, it's called beta 0j, and the j represents the different dogs. So what this is saying, BOJ, is saying beta 0, which can be different for each dog. So it's not a single value, it's potentially a value that can vary from dog to dog. And the way that ends up panning out is that the beta 0j is actually made up of 2 terms. So one is our regular beta 0, our regular overall level of vocalizations, but we also have this extra term in the model, which we've labeled U, which estimates the variability in the intercept across different dogs. Now if none of that makes any sense, it doesn't really matter. All I want you to grasp is the fact that we can let our intercept incorporate information about the fact that data comes from the same participants, and in particular what we're doing here is we're allowing the sort of overall level of vocalizations to be different across different dogs. So we're saying beta 0 is not a single value for all dogs, it's a value that varies from dog to dog, and in doing so we accommodate the repeated measures design. We can also, although we don't have to also take this step as well. But remember earlier on I said, well, look, it looks like the experimental effect differs for different dogs. So for, you know, Professor Nose, it looked like the training had had quite an effect, whereas for the venerable Dr. Waggy, not so much. We can also incorporate this into the model. We can incorporate the fact that the effective entity might be different for different dogs. And that's what this B1J represents. Now, we don't always fit this sort of complicated version of the model, but we can, if we have enough data. So again, the parameter estimate attached to entity now is made up of two components. It's made up of the component that we've worked with all term long, which is a kind of a beta 1 that applies to the entire sample and is a single value. But again, we have this this U value, which represents the variability in that parameter estimate across different dogs or different individuals if you were testing humans. So we've got a beta 1 that now incorporates the fact that beta 1 can vary from individual to individual. So again, it's kind of factoring in that the experimental effect can be different for different dogs. Like I said though, you don't particularly have to understand or process any of that to run the model, but I'm just explaining how the repeated measures element of the design gets factored into the linear model. So there's a few approaches to repeated measure designs. There's a sort of a simpler approach, which is the approach that we kind of go for on this module. And there's a more complex approach. The simple approach is to assume something called sphericity. So this is kind of an added constraint on the module, and if we on the model, and if we can assume this and estimate it and correct for it, then we can just kind of run a model as we've run other models and kind of forget about the fact we've got repeated measures design really. The other alternative is more akin to what I was just explaining on the previous slide, which is that we fit a slightly different kind of model known as a multi-level growth model, or just a multi-level model if you're not looking at things over time. And what this does is allows us to explicitly model different kinds of dependency in the error term of the model. Again, we don't teach you the multi-level model approach, which is the more complicated and more flexible approach. We just teach you the let's assume sphericity, estimate it and correct for it approach. So what is this sphericity thing? Well, sphericity is all about the differences between conditions. So what we have here is a table of differences. So the first column, alien minus human, is the difference in the number of vocalizations when sniffing an alien compared to when sniffing a human. So if we look, for example, at Milton, there's a difference of 1. So what we're saying here is when we look at the difference between how many vocalizations Milton made when sniffing an alien versus sniffing a human, there was a difference of 1. And if we look back to previous slides, we can see he made 8 vocalizations for an alien and 7 for a human, so that is indeed a difference of 1. So that's where that difference comes from. We can also see if we look at alien compared to mannequin, so 8 for an alien, 1 for a mannequin, that's a difference of 7. Alien versus shapeshifter, 8 for an alien, 6 for a shapeshifter, he'd have a difference of 2 there. Coming back to this slide then, so we saw for Milton, he's got a difference of 1 between alien and human, difference of 7, alien and mannequin, difference of 2 for alien and shapeshifter. And we can do the same for the other conditions. So look at the difference between the vocalizations for human and mannequin, that's 6, for human and shapeshifter that's 1, for mannequin and shapeshifter that's -5. So all these columns represent different scores, the difference in the number of vocalizations between pairs of conditions or pairs of entities. And we've done that for every single dog. We get this lovely table of numbers that I'm sure is exciting everyone. Now, if within each of these columns we worked out the variance in these differences, so if we worked out the variance across these scores, we find it's 5.27. And if we do the same for the differences between alien and mannequin, so what's the variance of these scores? It's 4.29. Now the assumption of sphericity is the assumption that these variances are the same, or roughly the same. So it's like the variance of the differences between conditions should be more or less the same. So the two columns that I've picked, looks like sphericity does kind of hold for that. So for alien versus human, we've got a variance of 5.27. For alien versus mannequin, we've got a variance of 4.29. They're roughly the same. However, if we now kind of come on to look at alien versus shapeshifter, there, when we look at the variance of those differences, it's huge in comparison. So we get a value of about 25. So that's about 5 times more than the previous 2 columns. So this would be an example of sphericity not being true, because the variance for alien versus shapeshifter is 5 times greater than the variance for alien versus human. So that's what sphericity is all about. It's basically saying if we take these differences in scores and we calculate the variance for each of those columns of differences, all these values should be roughly the same. And hopefully you can see for these data that is definitely not the case. So these data violate this assumption of sphericity. Now, so the assumption of sphericity, we've just seen what it is. It's that the differences between pairs of groups should have equal variances. If we work out the differences between scores in different pairs of experimental conditions and work out the variances, they should all be equal. We can estimate sphericity using a couple of methods, the Greenhouse-Geiser estimate and the Huhn-Felt, which I'm probably pronouncing terribly, terribly wrong, estimate. There are 2 different ways of estimating the degree to which you have sphericity, but in both cases, if the value is 1, you have perfect sphericity. In other words, the assumption is perfectly met. Values less than 1 mean that sphericity is violated to some degree or other. The further away from 1, the bigger the violation. So we can use the Greenhouse-Geiser estimate, or the other one, to work out the degree to which we've violated the assumption of sphericity. Happy days. So how do we do that? Well, this is the equation for the Greenhouse-Geiser estimate. And as you can see, it is basically f***ing horrible. So we don't really want to be doing that by hand, but this is the reason I put this up here, is just to show you that when you're in your darkest moments, struggling with R and wondering why the hell you are bothering to do it, then look at this equation and think, well, that's why I'm doing it, because it means I don't have to work out equations like this by hand. So you can estimate sphericity with some hideous equation that will take you through a space-time vortex into the bowels of hell, or you can let R do it for you and go and have a pina colada instead. So let's all choose that option. I mean, it doesn't have to be a pina colada, it can be a cup of tea if you prefer. So having estimated sphericity for us, what R can do, if we let it, is to multiply the degrees of freedom for the F statistic by one of the 2 estimates. And in general, we use the Greenhouse-Geiser estimate because it's the more conservative of the 2. And that's it really. We estimate how much we've violated sphericity by, and then we correct the degrees of freedom by that amount. So given that the estimate of sphericity quantifies how much we have deviated from perfect sphericity, what we're effectively doing is correcting the degrees of freedom by the degree to which we have a problem. Now remember that when sphericity is perfect, these estimates will be 1, which means the degrees of freedom don't get corrected at all. And when you don't have perfect sphericity, they will become smaller. The degrees of freedom will get smaller because they'll be multiplied by a value less than 1. And by getting smaller, it means that the test statistic, the F statistic, it's harder for it to be significant. So essentially you're making your test slightly more conservative. So the bottom line here is when you have a repeated measures design, you can probably ignore the last few slides in their entirety, but I've got to do something to fill up the 50 minutes. You should just routinely apply the Greenhouse-Geiser correction and forget about sphericity, basically. I mean, you can't forget about it entirely because I might put a question about it in the exam, but other things being equal, apply Greenhouse-Geiser and forget about it.
Sphericity, what a pain. When I think of sphericity, it really melts my brain. But I have Greenhouse-Geiser to help me on my way. Adjust the degrees of freedom and sphericity goes away. So how do we fit the model then? Well,
just like in the previous week, we can use the afex package and the alv4 function, and we use it in pretty much the same way. The only difference is with a between group design or an independent design, we specified a term here, which where the RM predictors was actually just the value 1. So we're just changing one little part of how we specify the model, which is this part down here, where we basically list the repeated measures predictors, and we have to also list the variable that represents the the ID of the participant. So in this case, the ID of the participant is the dog name. So we put that in there, and the repeated measure predictor, we've only got one of them on this occasion, was entity, so that's what goes in there. The rest of how we specify the model is exactly the same as when we use this function in a previous lecture. So we're predicting vocalizations from the variable entity. And that's it. It'll automatically set contrasts. You can get a built-in interaction plot, which we looked at in the previous lecture, but you don't get parameter estimates, you don't get diagnostic plots, you can't do robust methods. We don't teach this, so fall asleep for the next 30 seconds, but if you're interested, if you want a kind of a more flexible approach, you can use the LME4 package and a function called Elmer. It's a trickier option, and we don't teach it to you because it's very easy to get into very sticky territory very quickly, but this is akin, I just want to point out, this is akin to using LM that we've used for other linear models, really. So you would manually set your contrasts. It means you can get parameter estimates, you can get diagnostic plots, you can, with a bit of difficulty, get some robust methods as well. But we're going to stick with afex for the purpose of this module. So we can set some contrasts if we want to. So if the although afex will manually do contrast for you, we can override them. So this is basically what I'm saying here. We can override the manual contrasts. If the dog training has been successful, then what we would expect to happen is the sniffer dogs should make more vocalizations when sniffing aliens versus non-aliens. So our first contrast could very straightforwardly just look at the two alien kind of conditions versus the two non-alien ones. So that was, we'd lump together alien and shapeshifter because they're both aliens, but one's in humanoid form and one's not. And we could kind of mash together humans and mannequin because they are sort of things in humanoid form that are not aliens. So that could be our first contrast, kind of alien versus non-alien. And then we'd have to sort of subdivide these two chunks. So first of all, we've got a chunk with alien and shapeshifter, so we would need to split that apart. So we'd have a second contrast comparing alien and shapeshifter. And then we also need to split apart the human and mannequin group. So we could do that with a third contrast, which ignores alien and shapeshifter and compares human to mannequin. So that's a set of contrasts that would fit for this experiment. And using the rules for coding, which we covered in the lecture on contrast coding, we would get contrasts something like this. So contrast 1 compares alien, so they get the alien and shapeshifter get the same contrast value, and it compares them against human and mannequin, which have minus values because they're being compared against the other two. Contrast 2, we're comparing alien against shapeshifter, so notice one has a positive weight, one has a negative weight, and human and mannequin are ignored, so they get zeros. And for contrast 3, alien and shapeshifter are ignored, so they get zeros, and we set we set weights for human and mannequin. Again, notice one's positive and one's negative, which means they're being compared. You can look at where those weights come from by revising the contrast lecture. So in terms of the overall model summary, this is what we get out of afex. So we get our effective entity. These are our degrees of freedom, which you can see I have reported down here. This is our F statistic. We get an effect size, the generalized eta squared, and a p-value of 0.063, which is technically not significant if we use the the usual criterion. So we'd conclude that the entity sniff did not have a significant effect on the number of vocalizations by our sniffer dogs. But really small sample, so this would have been a massively underpowered study. And if we look at our effect size, our generalized eta squared, it's kind of telling us that the effect is reasonably big, because in fact The entity sniffed accounted for about a third of the variance in vocalizations. That's a pretty big amount. So even though we had a small sample and a non-significant result, it looks like the effect is actually quite strong. I mean, we wouldn't want to make too many great claims based on a sample of 8, but there's, you know, there's something worth investigating there, perhaps in another study maybe. So how would we interpret this? Well, the non-significant main effect, if we were just going to go with p-values and ignore the effect size, we're basically saying that these 4 means are, statistically speaking, at any rate, the same. So we're saying there's no kind of difference between this pattern of means that we see there. If we look at the contrasts, so we've got 3 contrasts, and you know, again, if you were gonna kind of take the p-value at face value on its own, you probably wouldn't look at these or probably shouldn't look at these contrasts, because you shouldn't break down a non-significant effect. But if you're placing some weight on the effect size, you might still be interested in seeing what the effect sizes are for these contrasts. And again, it looks like if we kind of look at the contrast that compares vocalizations to aliens versus non-aliens, the estimate itself is 2.75, and that is significant. So, you know, with, again, massive caveats on this, it doesn't look like there's something going on when dogs sniff aliens versus when they sniff non-aliens. When we compare their vocalizations between aliens and shapeshifters, it's not a significant effect. When we look at it between humans and mannequins, the effect is basically 0, highly non-significant. So it looks like there might, if we were going to replicate the study with a bigger sample, what we'd be looking at is the fact that it seems like dogs can maybe distinguish between aliens and non-aliens. They can't distinguish between an alien and a shape-shifting alien, you know, because they probably smell the same, they just look different, so that's reasonable. And they can't distinguish between a human and a mannequin, because remember, they've been trained to sniff aliens, so they've not been trained to sniff to kind of vocalize when they sniff humans. They've been trained to vocalize when they sniff aliens. So that's a condition where they weren't sniffing any aliens, so it's not that surprising that they gave the same number of vocalizations. If we'd had no prior hypotheses, we could also look at post hoc tests. Again, you generally wouldn't do this when you've got a non-significant initial result, but just to show you that you can. And this compares all different conditions to each other. So alien versus human and alien versus mannequin. They give us significant differences in the number of vocalizations. So that seems to suggest that dogs vocalize more when they're sniffing an alien compared to a human and a mannequin. When we compare aliens with shapeshifters, we get a non-significant difference. When we compare humans with mannequins and humans with shapeshifters, we get non-significant differences. And when we compare vocalizations when sniffing a mannequin and a shapeshifter, we get a non-significant difference. So again, the pattern here seems to suggest that the sniffer dogs do make more vocalizations when sniffing an alien compared to a human and a mannequin, but not when they're sniffing any other kind of combination of things. Now, when we use afex, we can't get diagnostic plots, so we don't really know whether our model meets the assumptions or not, but we can routinely apply a robust test instead. We can do this with a function known as RM ANOVA in the WRS2 package. When we do this, we basically get a robust F statistic with associated degrees of freedom and a p-value, which turns out to be non-significant. So the robust test backs up the idea that the overall test is non-significant, again with the caveat that this p is based on an enormously small sample. We can also get robust post hoc tests, which basically we're looking at whether the p-value is smaller than the p-critical value, and if it is, then that test is significant. Helpfully, this final column just tells us whether the significance is true or false. So if it says true, it means significant difference. If it says false, it means non-significant difference. And for all of these robust post hoc tests, it's saying non-significant difference, which suggests the training hasn't been that successful. But again, massive caveat over the small sample. Days, you're back! Good news, the sniffer dogs did well. Although the results were not significant, the sample size was, pretty small, and the effect sizes are looking strong. I'm optimistic.
We have intercepted another transmission.
It's more bad news, I'm afraid. Oh no. Show me.
Lazing Dirt, mighty leader, I have returned.
Ah, Tunic Lane. How's the shape-shifting training going?
Exciting news! I can do the hands! Look! I've got human hands! But I'm having a bit of difficulty with the face now. I can't stop my face from being green!
Why are you here?
Ah, well, I have intercepted a report from the humanoids. Take a look.
The humans plan to use sniffer dogs to detect us, but their early research shows non-significant effects. Good. Given our natural beautiful odor of putrefying bog water, I am surprised by this. But a p-value never lies. We can make things harder for those disgustingly cute, fluffy dogs by masking our smells with human pheromones and the scents of foxes.
Dogs love foxes.
Quick, Tunic, find me some humans and foxes that we might rub our bodies against them.
As you command, mighty leader.
I told you, not good news. They don't like dogs. What kind of evil creatures are we dealing with? Masking their alien smells with scents. Interesting. But I'm not sure it's going to fool our sniffer dogs. Let's do some more research. Okay, so the aliens are planning to use scents to make it harder for our sniffer dogs to sniff them out. Now, if we were going to do some research to look at whether this was, actually a viable plan, well, first of all, since our last experiment, we've managed to train a lot more sniffer dogs. So we've now got 50 of them instead of 8. So that's a more, slightly better sample. And what we're going to do now is we're going to get them again to to sniff different entities. But this time we're just going to use 3. We're going to use a human, a shape-shifting alien, and a lizard form alien. And we're also going to vary whether the entity was masked with no scent, whether their smell was masked with human pheromones, or whether their scent was masked with fox pheromones. So the dogs sniff all combinations of entities and scent masks. So each dog will sniff 3 humans. 1 human has no masking scent, 1 has a human masking scent, and the other one has a fox masking scent. They'll sniff 3 shapeshifters, 1 with no masking scent, 1 with a human scent, 1 with a fox scent, and 3 aliens, 1 with no masking scent, 1 with a human, and 1 with a fox masking scent. So each sniffer dog sniffs 9 entities in all. Again, we'd randomize or counterbalance the order in which they sniff them. And again, the outcome's a number of vocalizations during the 1-minute sniff. So this is a factorial design. We've now got 2 predictors, the entity they sniff and the scent mask that was used. Now the model here gets really, really complicated. Feel free to fall asleep at this point. Again, if we simplify things by ignoring the fact that both entity and scent mask will be represented by dummy variables in the actual model. So entity, we've got 3 groups that'll end up, or 3 conditions that'll end up being 2 dummy variables, and scent mask also 3 conditions, so that would end up being represented by 2 dummy variables as well. And for the interaction, you'd have the entity the entity dummy variables multiplied by the scent dummy variables, so you'd end up with 4 dummy variables representing the interaction. But let's ignore that for ease. If we pretend that entity is represented by a single predictor and scent is represented by a single predictor, and the interaction is represented by a single predictor, just to make things slightly more easier, we're basically saying the same thing as before, in that in its most complex form, we can say that the intercept is made up of 2 terms. It's made up of an intercept, like an overall intercept that kind of applies to the whole group, but also a term representing the variability in intercepts across different dogs, across the 50 different dogs. We can also say that the effect, so the parameter estimate associated with entity, so the effective entity, again there's like an overall group level effect, but we can factor in that there's variability in that effect across the different dogs. We can do that for scent as well. We can say there's an overall effect of scent, but we're going to model the fact that the effect of scent might be variable across different dogs. And we can also do it for the interaction. So we can say the effect of the interaction is an overall kind of effect, but we can also model the fact that there's variability in the effect of the interaction across dogs. This is a very, very complicated model. You wouldn't necessarily fit this version of the model because it's got a lot of terms in it. But at a bare minimum, if you've got repeated measures design, what we're effectively saying is that the intercept can vary across different dogs. So we're just acknowledging that overall levels of vocalizations can vary from dog to dog. And that's a kind of a basic way of factoring in the repeated measures nature of the design. So here are the data. They look very similar to before. So we've got our first dog takes up 9 rows this time because that each dog contributes 9 scores. So these are the 9 vocalizations for that first dog. The first 3 of them relate to when they were sniffing aliens. The first one was an alien with a fox scent applied. The second one was an alien with a human scent applied. And the third was an alien with no scent applied. Next 3 scores represent when that same dog was sniffing shapeshifters, again with a fox scent, human scent, and no scent. And the final 3 scores for that dog represent when the dog was sniffing a human, again once with a fox scent, once with a human scent, once with no scent. So each dog's contributing 9 scores, and we can scroll through these data to see there are like different dogs. They all contribute 9 scores. This is what the data look like. So when there is no scent, no masking scent at all, the pattern we see is the number of vocalizations look quite similar when they're sniffing an alien, so a shapeshifter or a lizard alien, and they're quite a lot higher than when they're sniffing a human. When a human scent is applied to the entity, then again it looks like there's a lot more vocalizations when they're sniffing some kind of alien than when they're sniffing a human. But when a fox scent is applied, the vocalizations are really quite similar for all 3 of these entities. So it looks like what's going on here potentially is that the human scent doesn't really make any difference at all. You get the same pattern of results to when no scent is applied, but the fox scent looks like it might make a difference. But it mainly makes a difference in creating more kind of vocalizations for when they're sniffing a human, which is kind of not what the aliens want. What the aliens want is they want the dogs to make fewer vocalizations when they're sniffing an alien, not more vocalizations when they're sniffing a human. So the fox scent, when it's applied to an alien, doesn't seem to actually make much difference. But let's see how that's borne out by the model. So now we've got a factorial design. So we have a main effective entity, a main effective scent mask, and the interaction between entity and scent mask. All of these effects are significant. We've corrected all of them using the Greenhouse-Geisser method, and you can see all the p-values very small. We've also again got these generalized partially to square values as well, which give us an idea of the size of each of the effects. So how do we interpret all of these? Well, first of all, repeat the mantra from a previous lecture. It's not sensible to interpret main effects in the presence of a significant interaction. So the fact we have a significant interaction means we can, to all intents and purposes, ignore the effect of entity and ignore the effect of scent mask, because they're not that interesting given that we know that each of those effects is moderated by the other. So what we can say from this is, well, basically report the interaction. So we can say the interaction effect suggests that the effect of entity on vocalizations was significantly moderated by what scent the entity was wearing. And we've got our degrees of freedom for that interaction effect. We've got our F statistic for that interaction effect, and we've got our p-value. We've also got an effect size of generalized eta squared. So the effect size suggests that the interaction accounted for about 24% of the variance in vocalizations not accounted for by the other variables. So, and that's a pretty decent amount. So we saw when we looked at factorial designs that we can use a simple effects analysis to break down this interaction. So first off, let's have a look at the effect of entity within the type of scent. So if we break it down and look at the effect of entity when no scent was used, when human scent was used, and when fox scent was used, what's the pattern of significance that we find? What's the pattern of results that we find? And in fact, unhelpfully, we find that when no mask was when no scent was used, there's a highly significant effect of entity. When a human mask was used, scent mask was used, highly significant effect of entity. And when a fox scent mask was used, also a highly significant effect of entity. So basically the effect of entity was significant in all three masking conditions. So that doesn't help us too much. What we can, what we could see from the graph is that the effect of entity was smaller when a fox scent was used, but it's still significant, still highly significant. So this isn't really that helpful. So let's do the simple effects the other way around. Maybe that will be more helpful. So what's the effect of scent within entity? So we're flipping this around to say, do we get an effect of scent mask when a human is sniffed? Do we get an effect of scent mask when shapeshifter is sniffed and when alien is sniffed? So when a human is sniffed, the scent that was worn has a highly significant effect. When a shapeshifter was sniffed, the effect of scent is highly significant. And when an alien was sniffed, the effect of scent was highly significant. So again, it's not tremendously helpful because basically the scent worn had a highly significant effect for all of the entities. So what do we do? It's not a particularly helpful finding. So what do we do in this kind of situation? Well, what we can do, we could do some post hoc tests across the interaction. Now the trouble is we've got 9 different means, and if we look at each combination of pairs of those 9 means, so if we compared every mean to every other mean, we'd end up with 36 post hoc tests, and it will be a bewildering befuddle of tests that's quite hard to kind of unpick. So we can be more selective with the tests that we do. So for example, we might choose to kind of look within each scent. So do post hoc tests within each scent. So within no scent being used, we do post hoc tests across these 3 means. So we'll end up getting 3 tests here: human versus shapeshifter, human versus alien, shapeshifter versus alien. Then we could move on to masking scent and do the same thing. So look at the effect, the post hoc tests for entity within when a human scent was worn, and then look at post hoc tests for entity when fox was the scent worn. So then we get another 3 tests here, another 3 tests here. So we'd end up with 9 post hoc tests rather than 36, which is a more manageable amount, more interpretable. We'd have to do less harsh kind of corrections for the number of tests that we've done. So that is one strategy you could adopt. When we do this is exactly what I've done here. So we're looking at when no scent was applied, what are the differences? What are the differences in the vocalizations between the different entities? So when we compare human and shapeshifter, significant difference. Human and alien, significant difference. Shapeshifter and alien, significant difference. So in other words, all the means are significantly different. When no scent is worn, dogs make more vocalizations than when they're sniffing aliens, significantly more when they're sniffing aliens compared to shapeshifters, significantly more when they're sniffing aliens compared to humans, and significantly more when they're sniffing shapeshifters compared to humans. So when no scent is worn, dogs can discriminate reliably between aliens, shapeshifters, and humans. What about when a human scent is worn? Again, comparing human and shapeshifter, highly significant. Human and alien, highly significant. shapeshifter and alien, highly significant. So when a human smell is worn to mask the scent, again, the dogs can still very well discriminate between the entities. So they give more vocalizations, significantly more vocalizations when sniffing an alien compared to a shapeshifter, when sniffing a shapeshifter compared to a human, and when sniffing an alien compared to a shapeshifter. So again, they're very successfully discriminating. What about when fox scent is worn? Well, when fox scent is worn, the human shapeshifter comparison is highly significant. So that suggests that they give significantly more vocalizations when they're sniffing a shapeshifter than when they're sniffing a human. I'm getting the direction of these effects from the graph, by the way, and also the sign of the estimate. When they're sniffing a human compared to an alien, there's also a highly significant effect. So they give more vocalizations when sniffing an alien than a human. However, when they're sniffing aliens and shapeshifters, there's no significant difference. So all the fox odor does, the fox scent does, is it stops the dogs being able to differentiate aliens from shapeshifters. But it doesn't stop them being able to differentiate shapeshifters from humans and aliens from humans. So they're still going to be very successful at discriminating between aliens and humans. They're just not going to be able to tell whether it's a shapeshifting alien or an alien, lizard alien. So again, this is not really what the aliens want. Basically, our sniffer dog training has been very, very successful when we look at it in a bigger sample. So looking at that profile of effects, we can say that when no scent is worn, mean vocalizations differ between all entities. Aliens elicit significantly more vocalizations than both shapeshifters and shapeshifters elicit significantly more vocalizations than humans. Happy days! This pattern's exactly the same when a human scent is worn. Happy days! When fox scent is worn, things change a bit. There are still significantly more vocalizations when sniffing aliens and shapeshifters compared to humans, but the difference between shapeshifters and aliens is not significant. So it messes up the dog's ability to distinguish space lizards from humanoid space lizards. So to sum up the sense, don't distract the sniffer dogs from detecting aliens compared to humans, but it does confuse them when they're trying to distinguish a space lizard in humanoid form from a space lizard in space lizard form. Now, if you want to test, look at diagnostic plots and robust models in a factorial repeated measures design, well, there is the face of a sad spaniel on your screen because you can't do it. And so that is the face. So when you're trying to do that and you're going, I want some diagnostic plots now, you're going to end up looking like a sad spaniel who is full of sadness because can't be done.
Lazzing dirt! Bad news! Bad news! Our invasion has been detected!
How is that possible? The p-value was greater than 0.05 and we smeared ourselves with human sweat and fox poo.
Apparently, the effect size was large. The sniffer dogs were better at detecting us than we realised. And the scents, they didn't work. And the dogs were so cute that we wanted to cuddle them and live in harmony with the puppies and the humans.
Cute? Cute? But puppies are hairy and tonguey and licky and disgusting.
Oh, but they're so nice to cuddle. Why don't you try one?
Yes, I like its ears. Perhaps we should try to assimilate rather than invade. But how can we? As a species, we are socially awkward, aloof, uncool, logically minded hermits. We cannot exist undetected in the humanoid world. They are so sociable.
Well, I think there might be a way. The humans have a shortage of people that have all of our qualities. They're aloof, socially awkward, hermit-like, logically minded. They're called statistics lecturers.